Hello, Astronomy. Welcome to our second and final video for Unit 3. So quick review, Unit 1, or Video 1 rather, we took a very deep dive into some physics about the EM spectrum, wavelength, frequency, Means law, cosmic background radiation, things like that. This video, we're going to keep it a little bit simpler, keep this a little bit shorter. We're going to do a history of the telescope and discuss different types of telescopes. So this is a picture. I think this is in Amsterdam, maybe. This gentleman is supposed to be Dutch. The Dutch are sort of credited with, I guess you could say, inventing the telescope. They were really good at grinding lenses and realizing that you can magnify objects using curved pieces of glass. So, no one person gets credit for inventing the telescope. You sort of just give the credit to the Dutch as a whole. Obviously, the first guy who gets credit for pointing a telescope to the heavens and discovering things was Galileo. We discussed this in a lot of detail back in Unit 2. Here you can see a mock-up of Galileo's telescope. Here you can see a drawing of him looking at the sky. So Galileo's telescope was based upon lenses, like we said. Telescopes that use lenses are called refracting telescopes. To refract means to bend, and lenses bend light. And you can see in Galileo's telescope, there's two lenses. There's one here called an ocular lens, or the eyepiece. Then there's an objective lens at the end, all right? Galileo's telescope was actually, you could get a mock-up of his for like less than $10 today. It was not a particularly powerful telescope. This kind of telescope, you can go to a store and buy one like this for 40 bucks. You can get a really good one for less than 100. Ones that look like this, just common backyard telescopes, are again refracting telescopes because they use lenses. If you notice this one, like this telescope, you are looking down into the eyepiece. There would obviously be a little mirror here to reflect the image up to you. This is just for comfort. If the eyepiece is coming down, like if you look at Galileo, this is kind of an uncomfortable position to be in, makes your back and your neck hurt. So having a little mirror here to reflect the image up to your eye is just for comfort. So the mirror in this one is not magnifying, it's just reflecting the image up to your eye. So there's a lens here, there's a lens here, and in this case, there's a little mirror reflecting the image up. This is a schematic of a refracting telescope. The objective lens is the big one. Here's the eyepiece lens. The problem with refracting telescopes are lenses are heavy. The more you can magnify the image, you need to have a bigger lens, right? And when you have a bigger lens, it means the focal length is bigger, this part F, which means as these get bigger, the lens gets bigger, which makes it heavy, and it has to be longer, a longer telescope. The telescope at Roper Mountain Science Center in Greenville is a refractor, and if you go see it, it's one of the biggest refractors in the country. That telescope, I believe, was originally from Princeton. It's it's probably upwards of 100 years old. Anyway, but it's incredibly long. Like it takes up the whole room because the lens is so big. So when lenses get that big, they get heavy and the telescope tends to wobble. And if you're trying to focus on something that's very, very far away and the telescope wobbles even, a nanometer, well, maybe not a nanometer, if it wobbles a millimeter, you're not gonna be able to focus on things. So making these telescopes big is just not incredibly practical. There's a limit to how practical these can be when they're really big. Okay, so skip ahead. So telescopes like this, these are called reflecting telescopes or reflectors. This is the kind that was invented by Isaac Newton. So if you look at this telescope, first off, just compare it to the refractor we saw earlier. The eyepiece is here. So it's toward the top of the telescope, and both sides of the telescope are the same size. Reflecting telescopes, this is they're called Newtonian telescopes sometimes because Newton invented them. This is a Newtonian telescope. So reflecting telescopes use mirrors to magnify. Now you've probably seen like a mirror in a makeup compact or a mirror in a bathroom where it makes your face look bigger, right? So a concave mirrors like this one will magnify an image, right? So Newton figured out that you can use mirrors to magnify. In this case, there's the primary mirror here, which is this one's curved inward, so it's concave. The secondary mirror just reflects the image up to your eye. There is a lens here. There is an eyepiece. So this kind of telescope does have lenses. But the big mirror that does the work is this one. And here's the deal. Light has to go through a lens, right? So if a lens gets big, the light goes through more lens, and that's just, there's a limiting factor in the size you can have for lenses. Light doesn't have to go through a mirror, right? Mirrors can be the size of a whole wall, and they can be, you know, a millimeter thin. So you can make mirrors much bigger, honestly, much cheaper, much more lightweight, that don't give you wobble, right? Again, a big lens gets thick. A big mirror doesn't get thick, right? So these kind, you know, if you look at this one, these are generally a little bit more expensive than a refractor, although you can get a good reflector for less than $100. You see they're bigger on the ends because that's where the mirror is. So in this case, the mirror is down here, the one that magnifies. You're looking through an eyepiece here, and there's some kind of internal mirror inside that's reflecting the image up to your eye, right? And this is open. You can put your hand inside it. It's open to the outside. This kind usually have weights here. This weight just helps to sort of find like the center of gravity of the telescope. So you have a weight, so it keeps it from wobbling. There's gears you can turn to move it, you know, slowly, incrementally. So you're not like, if you're tracking an object in the sky, you move it by hand, you know, you're gonna move it too much. Little gears you can turn allow you to move it like along with the rotation of the Earth, which is pretty cool. You can buy them where they're computerized, where they'll lock onto something and you don't have to do anything. It'll track the object in the sky for you. Those get pretty expensive though. Okay, so there's a Newtonian reflector. Great. Okay, so those were both optical telescopes because they detect light, have optics. So these are radio telescopes. So you've probably seen this kind of thing before with these dishes. So first off, you notice they're much bigger. The surface isn't a mirror because you're not reflecting light, you're reflecting radio waves. You'd have a detector like right here. Radio waves are fantastic to use to study because radio waves go through the atmosphere without much interference at all. You know, the atmosphere distorts light, it refracts light, it scatters light. If it's cloudy, you can't see through the clouds. If it's daytime, that's a problem with optical telescopes. With radio telescopes, you can use them any time of the day. If it's a storm, might not be ideal, but you can still see, you can see radio waves through clouds. And you can sort of like line them up in a row here, and they can be computerized where you can be monitoring the whole section of the sky using multiple radio telescopes. And again, these can get very, very big. A lot of times you've probably heard of SETI, S-E-T-I, the search for extraterrestrial intelligence. SETI is an organization that tries to find evidence of intelligent alien civilizations by monitoring radio waves. So the idea here, we use radio waves to communicate. We've been doing that for, well over a century, for radio shows, TV shows, you name it. And those radio waves escape into space. So think of a broadcast of I Love Lucy from the 1950s. That's now over 70 years ago. So those broadcasts have gone 70 light years into space. The nearest star is only about 4.5 light years away. So the furthest evidence of humanity would be our radio waves traveling through space, which go at the speed of light. So the idea here is let's point these at other stars and see if we can find artificial radio signals, which would be an indication of a civilization. Nothing has been found so far. There have been some interesting false discoveries. There's a famous book called Contact by Sagan. Carl Sagan is made into a movie with Jodie Foster I think it was in the late 90s, which is about this. She detects a radio signal coming from a nearby star, which is an alien civilization communicating with us. Anyway, so radio telescopes, it's not just looking for aliens. It's also, you can point a radio telescope at a star or the sun to detect, what kind of radio signals or transmissions the star or whatever is producing. All right. So this is the biggest radio telescope. This is in Puerto Rico. This is a radio telescope that's built inside a crater. It's called the Arecibo Radio Telescope. Sad news. So this picture is taken in December 2020, and you can see it's collapsed. So this is Puerto Rico. So after Hurricane Maria a couple years ago, and after several earthquakes, the support struts, these cables that hold the telescope, and here you can see the image beneath it, gave way and the telescope collapsed. So it was said to be decommissioned. And when this happened in December of 2020, there were no plans to rebuild it. The structural engineers, it was too dangerous to even like try to rebuild it. Now, since then, actually, I've recently heard that Puerto Rico has committed itself to rebuilding it. So we'll see if that actually happens. But the Arecibo Observatory was a very famous observatory. It was built in the 50s, I believe. Yeah, obviously really cool, and it was very tragic when it collapsed. Anyway, moving on. Okay, let's go into space. So this is the infamous Hubble Space Telescope. So telescopes are great, but when they're on Earth, with a few exceptions, the atmosphere blocks light, the atmosphere blocks X-rays, it blocks a lot of ultraviolet, which is good for us. We want it to block ultraviolet. But a lot of the light that gets to Earth is blocked or distorted by the atmosphere. So for a long time, people were like, well, let's put a telescope in space. The Hubble telescope is nowhere near the biggest telescope. It's about the size of a school bus. There's way bigger telescopes on Earth, but because it's in orbit, there's no atmospheric distortions. It's not that it's closer to anything in space. It's, gosh, I don't know, 200 or so kilometers up, which doesn't make it closer to anything that much. But the fact that it's beyond the atmosphere is why it's so cool. The Hubble telescope is named for a scientist named Edwin Hubble. We're going to meet Edwin Hubble in Unit 5 or Unit 6. I can't remember which one. He was probably the most famous astronomer of the 20th century. Why he was so famous, we'll see later. He advocated for a telescope in space. He obviously, I think he'd even passed away by the time the Hubble was actually launched. He did not build it, but it was named for him because he was a very influential astronomer, especially when it comes to understanding the origin of the universe. Okay, so the Hubble is a reflector. It has mirrors. The Hubble can also detect other types of other parts of the EM spectrum, about the size of a school bus. So the Hubble has a very complicated story. So the Hubble was launched, and we're going to see more of this in class when we do the space shuttle. In 1990 on the space shuttle, the telescope is inside the cargo bay here of the space shuttle. This is 1990. Very famous, very important mission. And when it got into space, they deployed it. And a couple of days later, the scientists were sitting in mission control on Earth or wherever to look at the first couple of images from the Hubble. And the deal with the Hubble is it was designed to see deeper in the universe than ever before. The Hubble was going to answer the question, where does the universe come from? The further deep you look into space, you're looking back in time, right? So if you're looking at a star that's 5 light years away, that light's been traveling through space for 5 years before it gets to your eye. So you're seeing the star as it appeared 5 years ago, right? So looking deep into space is looking back in time. So the Hubble gets launched, and the first images come back, and they're blurry, right? There was a sort of famous political cartoon at the time of the scientists like peer down, looking at the computer screen, and the little thought bubble says, "Well, maybe space is blurry." Of course, space is not blurry. The telescope had a problem, and the problem was, and this was a huge controversy, it was that the primary mirror, the term used was a spherical aberration, that the curvature of the mirror was off. It was less than the width of a human hair. It was a tiny, tiny, tiny bit that the curvature was off. But basically, the Hubble telescope needed glasses because the focal point of that telescope was off because the curvature was off. And this obviously was like a $1 billion mission, multi-billion-dollar mission. It took years and years and years to get in space. And the deal with the Hubble, there were ways to correct for that, but the promise was largely lost. At least they thought it was going to be lost because the Hubble needed glasses. So the size of the Hubble prevents you from bringing it back to Earth. Going up, you're going much slower than coming down. So bringing the telescope back down to Earth, it would have been too dangerous to have it in the shuttle. So in order to fix it, you're gonna have to fix it in space. So it took a couple of years. In 1993, so about 3 years later, we sent the first Hubble Repair mission. And this was by far the most ambitious NASA mission to date. There were a series of spacewalks planned. One, they wanted to, basically give it glasses to correct. They didn't change the mirror, but they put an instrument in front of the mirror that corrected the light, basically like glasses. They had to replace some of the solar panels, other instrumentation, and it took about a week or so. Actually, it was more than a week of multiple spacewalks to prepare it. And this was a big deal because we had done spacewalks in space, like going back to the Gemini program. We had to do spacewalks to fix the Skylab, right? But we hadn't done any kind of like complicated, fancy repair missions in space like this. So this was a huge undertaking. And you know what? All the boxes got checked. We fixed it. Since then, we have done several repair missions of the Hubble. Not so much repair, but upgrades. Only the first one was really repair. And the Hubble was never meant to last. When it was launched in 1990, so that's over 30 years ago. It was never meant to last as long as it has lasted. But because we've been able to repair it and upgrade it, it's been a huge success. In units 5 and 6, we'll talk more about what the Hubble has discovered in terms of the origins of the universe. So we'll save that for later. But yeah, it began as a massive NASA disaster and has ended as one of NASA's greatest success stories. Just another image of the Hubble. This is another image of the repair. I like this one because you can see how like the Hubble has innards. Like there's computer panels and there's machinery, and there are things called gyroscopes. Gyroscopes help you stabilize like where you're pointed to, that from time to time need to be repaired. Okay, so that's the end of Unit 3. We're going to end it there, and hope that was helpful, and I will see you guys next time.